When you're writing a code, especially when you're writing a code for a computer simulation, the topic of efficiency eventually comes up. For this reason, I would like to show you several aspects about how to write efficient code and optimizing code using an example. You can find all the files that I'm showing you here in this and the other videos when you go to the link in the description of the video. Now, to show you these different concepts and aspects, I want to use a very specific example, and let me first introduce you that example before we go to the actual performance discussion. So what I'm using as an example here is a simulation of a chain of balls. So we have these classical red balls with a certain mass. The position of these balls is determined by the variable vector xi. And these balls are connected to their neighbors through springs. And these springs are described by both a spring constant, which I denote as k, and by the distance in which they are in equilibrium and rest, and that is called d rest. Now, you could see this example here. This could be, for example, a very simple model of a guitar string, for example. So what I want to do is I want to write a simulation where I keep the outermost balls fixed and I can have an arbitrary initial position of these different balls in the middle connected to the springs. The physics simulation itself is not very hard because if it's spring, we actually know what the potential energy is. So this is given here, and from the so this is essentially given by the 1/2 times the spring constant times the deviation of the spring from the rest distance, and from that we can also very easily calculate the force that is acting on one ball from the two neighboring balls. Yeah? So remember, those springs are always only connected to the neighbor, so every ball here feels a force due to the spring connecting to its neighbors to the left and to the right. Well, as I said, we want to keep the two outermost balls fixed. So what you can do in the code is you can do this by forcing the forces at the edge to be exactly 0, because then we know that the balls will never move if they were in rest initially. And with these forces, we essentially have to solve the Newton's equation of motion then. Now, I have implemented this in a little module that is called simulation.py. Let me just briefly show it to you here. It's nothing very deep. So we have here the simulation routine where we start with 0 velocity of all balls, and then we have a loop over times, and in every instance of the loop, we're first computing the force due to the springs. So this is a separate function, which I'll use next. And then we're using here a so-called symplectic Euler method to do the time evolution. Yeah? So, and that's pretty much it. And then the new position is appended to a list and returned at the end. And at the end, the simulate function returns a whole list of position arrays. And with that, we can track how these balls move in time. Now, the most important part here is calculating the force due to the springs, and that I do here. So I write again a for loop, looping over all the balls that we have here. And in every case, I'm calculating first the distance vector to the previous and to the next ball, and I use that then to calculate the distance between them. And then knowing the spring constant and the rest distance, which are global variables in that code, I can then compute the force acting on that ball. And that function returns that force. So let's have a quick look at what that simulation does. Let's just quickly run it. And let's look at an example simulation, just to know just to see what the simulation is doing, and to see that it actually does a useful thing. So I'm making an initial position of my balls where I have a displacement in this fashion, in this linear fashion, and a little bit asymmetric. So you could actually imagine this is, picking a guitar string. This is when I just start to pick the guitar string a little bit away from the middle. And we can now run the simulation, and then we can just make an animation from the result to see how this chain of balls is moving. It takes a little while. So actually, in this case, making the animation takes actually longer than the simulation. That's actually something that happens more often. Plotting can actually take much longer because there's essentially these are all Python functions. So these are typically not super fast actually. So let's have a look. So here we have these initial positions of the balls. Now if I evolve it in time, we see, well, this somewhat complicated movement of these chain of atoms. Okay, now this was just to show you that, well, I'm actually doing a simulation that is sufficiently complex that it makes sense to actually do a simulation. So this is actually a problem that makes sense to do. Now comes the question of efficiency. And now, well, the first time that we have to ask ourselves, how long does the code actually take? So let's have a look in this case. So we can use this magic here, the 2 percentage signs. So that's an IPython magic. That's what it's called. If there's 2 percentage sign, it means it applies to the whole cell. If there's just 1 percentage sign, it means that it just applies to this one line. Here in this case, the time magic just tells us how much CPU time our simulation will take. So let's just run it. So the code took about 3.4 seconds to complete. Is this now good or is that bad? Now that really depends on what you want to achieve with that code, and especially how often you want to run it. Imagine that this is a code that you only need to run a few times, then 3 seconds probably pretty good. If you want to run it 100,000 times, then it's probably too long. So it really depends on what you want to achieve with the code. Now let me emphasize, what I tried to achieve so far was to get a code that works and that I can write and I can verify that it's correct. Now this, of course, always comes first. You want to have a correct code. If it's efficient and wrong, that doesn't help you. So correctness certainly always comes first. But whether now it makes time for me to put effort and time into optimizing the code really depends on what I want to achieve with it. So you always have to weigh this effort that you need to put into optimizing the code versus the time that you gain by more efficient code. In particular, if you want to optimize something, and that's for the sake of this tutorial, let's just assume that I need to optimize the code. It needs to be faster for me. Now you want to do the optimization in the most efficient way for yourself. And in particular, what this means is that you should probably not just go through all your code and try to think of more efficient expressions everywhere. I mean, this probably would, in most cases, you would try to optimize something which actually doesn't take a lot of time. In fact, there is a very famous quote saying premature optimization is the root of all evil. And what that really means is that you should first figure out which part of your code is most rewarding to optimize. So which part of your code takes the most time and could therefore gain the most from optimization. Now, this current example is of course not very complex, and you might be able to tell here directly which part you should optimize. But if you have a more complex project, this is not so obvious. But luckily, there are tools that can help you figure out which part of your code takes the most time, and this is called profiling. And what I want to do now is I want to show you a couple of tools that can do this profiling for you now specifically for Python. The first profiler I want to show you is the so-called line profiler. It's probably the most user-friendly of the profilers I'm showing this video, but it can be a bit tedious to use for a more complex project, and we'll see in a second why. Now, this line profiler is a Python module. If it's not installed on your computer, you might have to install it, for example, by executing pip install line profiler. Now, what does the line profiler do? It basically shows you for every line of your Python program how much time it takes. So in order to use it, we first need to load it. So we do this with this command $% load x line profiler. This allows us to use again, notebook magic to profile our code. So just like the time command that we had before, we now get a new command $lp run, which uses the line profiler to take a profile of the expression that we're executing. So here we are applying it to our simulate function. So we're just running the actual simulation. And for the line profiler, we need to specify which function it should profile very explicitly. And in this case, what we say is, well, of course, it makes sense to profile the simulate function itself. So we can do this here. We can say -f simulate, and then it will profile the simulate function. Let's have a look at the output. So we run it, and then we get an output. What we see here on top is it says total time 4.7 seconds approximately. We see that this is actually longer than the 3.4 seconds that we had before. The reason is that the profiler adds code to your code to time it, to keep track of how much time is spent in which part, and that generates a certain overhead. So this is completely normal. Now the line profiler now will here list indeed all the lines of your program. Well, in our case we have the doc string, so because I magnified it quite a bit, here the doc string has lots of lines which are broken across the window here. But it only anyways gets interesting here in the part which is about the code. And then we see these different columns. And well, let's go one step back. The most interesting part is here. So we have the last column just in front of the code is the most interesting because it tells you which percentage of the total time is spent in that line. Then there's also other things like, for example, how much absolute time is being spent here. But if you go here, what we actually see that in this particular code, 99.6% is spent in the Spring Force function. So this gives us a very natural candidate to optimize. Note that the other commands that we have inside this loop, they take far less time, although they're actually executed as often as Spring Force. So the first line here is how often the code is actually being executed. So 2000 times, that's the number of time steps that we have here. But essentially all the time is taken in Spring Force. So here we have a clear answer to our what would make most sense to optimize, because essentially all the time is taken in Spring Force. Now it can of course be interesting to also look into what takes how much time in Spring Force, right? For example. So we can also do that. We can also run the whole simulation and tell the line profiler to look only at the Spring Force function. What we need to do here is, if I execute it with just, what we had before and just say here -f Spring Force and execute simulate, it will actually not work because I do not know this word Spring Force, because it's not imported in a Python file. So what you can actually do here is you can just import the whole simulation package, and then you can say -f simulation.springforce. And when you run it, then it takes a while, of course, as before. Now it timed the Spring Force function, and there, well, we see a more complicated pattern now. So now here there's more lines that take a similar amount of time. Actually, in this case, this doesn't already help us so much anymore, because what we'll see is, there will be different approaches to optimizing this. And there's no clear single point which we should optimize. Huh? So here it probably makes sense to more say, we have to rethink this whole function by itself. Just to mention, you can also actually also profile two functions at one time, both the simulate and the spring force function. That's also possible. Just to mention that. Now, if you want to know more about this command lp run, you can always do this magic command and then with a question mark, and it will actually give you a doc string and tell you what kind of options there are. So this works for all the magic commands, also in the notebook. Okay, so this is the line profiler, and for our particular example, it gave us immediately the right answer. We need to optimize the spring force function. Now, I said that it's not that useful to use this line profiler if you have a very complex code which calls many different functions from different places, because here in our case the spring force function is called only from simulate, but imagine it's being called also from other functions, so then it's not so transparent anymore. The line profiler only gives you like a local view of how much every line takes in one function. It doesn't give you a global function of like where does your code globally spend most time in. So for this, it's better to use a different kind of profiler. So we'll also now apply it to this example program. And in particular, there's a built-in profiler into Python, which you can right away run with the magic command prun. So we can do that. We can run it, and we can look at the output again. And what we now see here is an output which, if you look at it first, it looks very confusing. And in fact, before I want to go to that particular output and also see how we can make sense out of it, I want to first use an additional tool on top of that to make that profile from the Python profiler into a graphical representation. And this is I'm still using the exact same profiler, but what I'm now doing is I'm now saving the output of this profiler, so not just a text output, more information than it generates, by using the argument -d and then a file name into, I'm saving that into that file. So I need to run that. And then I'm using a different command, a shell command, which is called gprof2dot, to make a nice call graph, which I can more easily interpret. So gprof2dot you might have to install using pip install gprof2dot. I'm also using a second command called dot. That's in a package called graphviz. And what I'm doing now here in this cell is that, so the exclamation mark means I'm executing a shell command. So let's not go into details how this works with the shell, but let's just say this whole line, what it does, it turns the profile that is saved in profile.pstat, which we just saved before, into an SVG file, and makes a nice call graph out of that. And then the next two lines, I'm just importing this SVG file now into the notebook, but of course you could just as well look at from the file system. You can also save it as a PNG file, for example. Then we'd have to replace here SVG here and here with PNG. So let's execute that. Yeah. And what this outputs is a so-called call graph. So it basically shows you in a graphical way what is called from where. And there are some funny things that you see in the beginning, which is here like built-in method built-ins.exec. That's actually more or less saying, well, that's like the notebook. That's a cell that you executed your stuff from. And that calls once the module, the module simulation. And we see here the 100%, which means, well, that takes 100% of the time. Well, that's just because now we're just calling stuff sequentially, essentially. And there you see, so basically it goes down a couple of steps until it gets to the simulate function. And the simulate function, it calls now SpringForce. And here we see that it says, well, it spends 99.6% of the time in SpringForce, and it's called 2000 times. So that's the same information as we had from the line profiler. And then SpringForce calls other functions. So actually here we see, well, it calls, well, it also looks a bit cryptic. It says array function internals sum and array function internals zeros like. That is NumPy. So this is the NumPy functions. And if you look back, we see, well, actually we had here, you know, we had npSum and npzeros like in our code. And for example, npSum takes 38% of the time, for example, here. There's of course other NumPy expressions, but they don't actually turn up here in this call graph. So here, you know, you get a more complicated view of what or a more a view that can also handle a more complicated situation, and shows you graphically, you know, in which part of your code a lot of time is being spent. Now that we know that, and that we also, you know, maybe we're not so afraid anymore about these funny looking names here, we can actually go back to our original prun output, and we will actually see those things back. So, well, we see here simulation.py SpringForce. So that is the function that they have been calling. And what this whole thing is being ordered now, it's being ordered by internal time. So internal time, that means that is the time that is being spent inside this function, excluding calls to external functions. Yeah. So that means that here it says, you know, 2.5 seconds it spends inside this function, and you know, in the rest of the time it spends inside these NumPy functions. There's the second column, which is sometimes even more important. That's cum time. That's accumulated time. So that's the total time it spends in the function and in all the functions the function calls. So that would be the same kind of time that we saw in the line profiler before. So now it's sorted according to internal time, and still we see that most of the time is spent in SpringForce. You can also order it according to other things, and again, here can be useful to look at the documentation. So in prun, for example, here with the -s command, you can sort it, and for example with the -s cumulative, you can sort according to cumulative time. We can do that here. And then we see a similar output as we had in the graph. So it starts with this built-in method, built-in exec, which is the notebook essentially. And then we see, well, of course, it spends almost all of time in simulate itself. But then we also already see that that still, you know, it spends most of the time in SpringForce. Yeah. So we now see again the same information that essentially SpringForce is the thing to optimize. Now, as for optimizations, there are different possibilities how to do that, and I will show you some examples in the other videos.